So section 21 is on the derivatives of log functions and on something called logarithmic differentiation. All right, so the derivative of natural log is super simple. The derivative of natural log of x is 1 over x. So this might clear up some confusion. Maybe you guys had questions about, oh, the derivative of x cubed was 3x squared, and the derivative of x squared was 2x, and the derivative of x to the first was 1x, and the derivative of x to the 0, you're like, oh, it's going to be, oh, what did I do? 1. Sorry, I'm skipping ahead, I know. 1x to the 0. So you're like, well, what thing is going to give you an x to the negative 1? If you have x to the 0, it doesn't give you an x to the negative 1, right? X to the 0 is just a number. Its derivative is going to be 0. So a lot of people are like, well, how do you get that? If you have x to the negative 1, well, it's negative 1 x to the negative 2. How do you get something that has an x to the negative 1 as a derivative? You have natural log. Okay, so natural log of x has a derivative of x to the negative 1, or 1 over x. All right, so you definitely need to know this. Very important. Okay, so likewise, like we talked about last time, you could have chain rule problems that involve natural log. So if you have natural log of x squared plus 10, right, it's in the form of natural log of u. So when you take the derivative of it, it's going to be 1 over the u, so x squared plus 10. But we need to multiply by the derivative of u. So what's the derivative of x squared plus 10? 2x, exactly. So you have 2x over x squared plus 10. Because it's not just in the form of natural log of x, it's natural log of something other than x. So we learned the rule for just natural log of x. All right, so this one is in the form cosine of u. So when I take the derivative, it's going to be negative sine of the u. So negative sine of natural log of x times the derivative of u. So the derivative of natural log of x, 1 over x. All right, so the next one, we have natural log of sine squared of x. So there's a couple different ways that you can do this. So we can notice that it's in the form natural log of u, and when we take the derivative, it's going to be 1 over the u, so sine squared x, times the derivative of sine squared x. So off to the side, if you need to say, okay, y is equal to sine squared x. So that's going to be sine of x squared. If that helps you to take the derivative of sine squared x, that's fine. So what's the derivative of sine squared x then?
2 cosine x sine x.
Yep, 2 sine of x to the first, and then times the chain, cosine of x. And what's going to happen is your sine of x is going to reduce out, so you end up just getting a sine of x on the bottom. And we would write our final answer as 2 cotangent of x. Okay, but there is an easier way. And that's what can be frustrating about this section, because sometimes you spend a lot of work, a lot of time finding answers, and then it's like you check your work with your friends, and your friend's like, oh, I just did it this way. And you're like, dang it. I spent like 10 minutes on that problem. Don't let that be you. So the easier way is to think about y equals natural log of sine squared x as being natural log of sine of x squared, and bringing that squared to the front. So natural log of sine of x. So what did I do there? Why am I allowed to do that? No, it's not a derivative. I haven't taken the derivative yet. Yeah, the log rules say that if you have a power, you can bring it to the front, right? That's all I did. It's just a log rule. Now I take the derivative. So when I take the derivative, the constant's out front, and the derivative of a natural log of sine is 1 over sine times cosine. So you end up still getting 2 cotangent of x. Okay, so that one didn't save a ton of time, but there are going to be ones that are much more difficult that will save some time. So let's use that on this next one. So before I start the problem, I rewrite. So instead of doing natural log of x to the 1/5, I'm going to rewrite it as 1/5 times natural log of x, exactly. Now when I take the derivative, I have 1/5 times the derivative of natural log of x, 1 over x. So our final answer is 1 over 5x. Now if you had done the long way, it would still work out to be 1 over 5x. It would just be a little bit messier. So you would have y prime equals 1 over x to the 1/5, and then you would need to multiply by the derivative of x to the 1/5, which is 1/5 x to the negative 4/5. So you'd have 1 over x to the 1/5 times 1 over 5 x to the 4/5 And if you notice x to the 1/5 and x to the 4/5, if you add their powers, you get x to the 1, right? So it works out the same. You end up getting 1/5x. Okay, so it works. All right, so I told you guys we would often have problems with, say, finding absolute max, absolute min. So we have another one of these. So it says find the absolute minimum of f of x equals x squared times natural log of x. So when we do this, we find the derivative, we set it equal to 0 or undefined, right? We find critical points and put them on a number line. So I'm going to find the derivative. So first is x squared times derivative of the second is 1/x, right? Because I'm thinking of it as x squared times natural log of x. I'm doing the product rule. Plus derivative of x squared is 2x times natural log of x. So x squared times 1/x makes x. And we're trying to set it equal to 0, so I notice I have a GCF. Okay. So I can pull out an x, so I have 1 plus 2 natural log of x. And I set each piece equal to 0. So I have x equals 0 and 1 plus 2 natural log of x equals 0. So I subtract the 1 over and divide by 2, so I get natural log of x equals -1/2. So what's x equal? Log base e, right? So it's log base e of x, so it's going to be e to the -1/2 is equal to x. Yeah.
Impossible to log something and get a negative?
No. You can take the log of something and get a negative out, but you can't take the log of a negative number. Does that make sense? Okay. Because the graphs for log look like this. You know, so if you take, like, you can get an outcome of a negative number, like a y value that's negative. All right. So we put these on the number line, and we're testing them in f prime. So I have 0, and I have 1 over e to the -1/2. Or sorry, not 1 over. So it's e to the -1/2, which is 1 over the square root of e. And that's approximately 0.607, I think I found in the last class. So we're going to test on the left, in the middle, and the right. So Jack brought up a good point. He said you can't take the log of a negative number. So if I try something on the left of 0, it doesn't work. Because I'm testing it in the derivative, right? I'm testing it in one of these. And I would have to take the log of, natural log of a negative number. So that doesn't work. So anything over here is undefined. All right, so let's say I try 1/2. So if I do f prime of 1/2, I get, let's see, 1/2 plus 2 times 1/2 is 1 times natural log of 1/2. Natural log of 1/2 is like -0.69 something. So plus 0.5 is going to be a negative number. So we get a negative there. Maybe I should just do a minus. Just do a minus. That's what I usually do. All right, and then if I try f of, let's say, 1, I get 1 plus 2 times natural log of 1, which ends up being a positive number. Yeah. Wow, thank you. I know, Evan's on top of his game these days. He's got 3 points in the last 3 days. All right. So what this means about f of x is that f of x is decreasing, right? The slope is negative until you get to 1 over square root of e. So you're going down, and then you go up. And at 1 over the square root of e, the slope is equal to 0. So it's kind of tapering off. It's like making like a parabola shape there, right? And giving you a slope of 0. So what does that mean? It means that we have a minimum at 1 over square root of e. Okay? So the way we write this is we say absolute minimum of something at x equals 1 over square root of e. So I want to know how low it goes. So how low something goes, I want to find its y value. So now I go back to the original, and I find 1 over the square root of e. So I'm going to do 1 over the square root of e squared times natural log of 1 over the square root of e. So this becomes 1 over e times, what about natural log of 1 over the square root of e? You guys had a similar one on your homework where it was like natural log of 1 over the 5th root of e to the 7th or something. Did you guys get that one? Yeah, because this one, the one that was on your homework, was natural log of e to the -7/5. So your answer was -7/5. So the same idea here. This is natural log of e to the -1/2. So it becomes just -1/2. So we get 1 over e times 1 over, or yeah, 1 over 2 with a negative. I know. I got it. So I get 1 over 2e. I'm struggling. All right. So if you did not know how to do that, then you hope and pray, oh, please let this be the calculator section where I have this question, because then you can just round to 3 decimals. But if it's not, you're out of luck, because you don't know your rules of logarithms, right? So you got to know those rules. It's usually not on the calculator part. All right, so it says we know that log base a of x can be rewritten using the change of base formula into natural logs. We like natural log, because if we're taking the derivative of natural log, it's super simple. It's 1 over x, right? So we like that derivative. So if we can write this in a different form, then we're good. So we're going to rewrite it as natural log of x over the natural log of a. Remember, the subscript goes down, the other number goes up. Okay? So if I have y equals log base a of x, I rewrite it as natural log of x over natural log of a. The natural log of a is some constant. A is a number. So natural log of a is a number. So what I'm going to do is I'm going to pull that constant, 1 over natural log of a, out front. So it's like that. So this is all a number. So what if I had, 5 times natural log of x? What's its derivative? You guys got that down. It's going to be 5 times 1 over x, right? So what's the derivative of this? Y prime is going to be
X, natural log of a.
it's 1 over natural log of a times 1 over x, so it's 1 over x natural log of a. Are you just looking below here and seeing this? All right, so it's 1 over x natural log of a. So the reason that we get this is because of the change of base formula. So you can think through the change of base formula, or you can memorize this. So when you see something, like y equals log base 5 of x, you can know right away what it is. You can say, oh, the derivative is going to be 1 over x, just like how a natural log starts, 1 over x. And then I tackle on a natural log of the base, natural log of 5. Okay? You do need to know those quite quickly, because you will have a derivatives drill in your near future. So you should know those.
10 seconds later.
All right, so if you don't know this, make sure you put it on a note card. All right, so here we go. Now I forgot to print them today. It won't be today. I would guess on Monday. All right, so differentiate the following functions. Look for tricks to make this easier. Always look for the tricks with logarithms. It can save you, a multiple choice question is supposed to take you like 2.3 minutes. Maybe you spend 7 minutes on one question when it really took you 30 seconds to do if you realize there was a trick. Does this make sense? So don't waste your time. These are big time wasters if you do it the wrong way. All right, so here we go. So f prime of x. Do you guys remember the derivative of 5 to the x?
Times natural log of 5.
5 to the x times natural log of 5. Good job. All right, and then what's the derivative of log base 3 of x? 1 over x natural log of 3. Okay, that's it. What about the next one? Natural log of e to the 4x. Can I rewrite it?
4x.
Oh, yeah. So what's its derivative? 4. Done. Took you all of 5 seconds. If you did it the long way, it takes you much, much longer. Don't do that way. All right, so how about something like this? We have y equals log base 2 of 4x squared. So if you don't see that there's a shortcut, there actually is. If you don't see it, then we do it this way. We say y prime. I'm going to have 1 over, this is in the form log base 2 of u, so its derivative is going to be u, so 1 over u, and then natural log of 2. And then we multiply by the derivative of u. So the derivative of 4x squared is 8x. And we simplify. So we get a 2 on top, we get an x on bottom, natural log of 2. Okay, here's the other way. And it's not necessarily a lot easier. I mean, it involves a lot of work before you take the derivative. So if I have log base 2 of 4x squared, I'm going to rewrite it. So I have log base 2 of 4 plus log base 2 of x squared. Log base 2 of 4, you actually probably know what that number is. What is that number? 2. What's its derivative? 0. So even if you didn't know, if it was like log base 2 of 7, you're like, I don't know what log base 2 of 7 is. But its derivative is 0. It's a number, right? So it doesn't matter what this is. It's just a number. And then this 2 can go to the front, right? So we have 2 plus 2 times log base 2 of x. Okay, so we've now simplified y as much as possible. Now we take the derivative. So y prime is going to be 0 plus 2 times 1 over x natural log of 2. So 2 over x natural log of 2. Is that the same thing? Mm-hmm. Yeah, so really, I mean, that one's not much easier because you still have a lot of work to do before you take the derivative. But if you're really familiar with those log laws, some of these problems can be much, much shorter. All right, so like this next one. I've done this one the long way. It's not so fun. There's the product rule involved, right? And then we have a square root of x, so we need the chain rule. It's not fun doing it the long way. If you notice that there's a shortcut, we do it. So when we have square root of x, isn't that just x to the 1/2? So it's going to be 1/2 log base 10 of x. And the 1/2 and the x cancel, so I get x times log base 10 of x. Now it still involves the product rule, but it's a much cleaner product rule. It's not as hard. Now I take the derivative, so y prime equals x times the derivative of log base 10 of x. So 1 over x, natural log of 10, plus derivative of x is 1 times log base 10 of x. So we get 1 over natural log of 10 plus log base 10 of x. And I've told you time and time again that the AP writers are terrible, and they always put things in different forms. This is one that they would definitely put in another form. They would combine your logarithms. So they would rewrite log base 10 of x with a change of base formula as natural log of x over natural log of 10, and they would combine them. So they'd have natural log of x plus 1 all over natural log of 10. Okay, so look for things like that. Your answer may be slightly different, and if you don't have a calculator, it's often hard to tell which one's the same. Like if you had a calculator, you could just plug in something random for x into each of your choices, right, and check to see which one's which. All right, so this one, number 5. So we're going to try to separate it if possible. So I have log base 5 of x plus log base 5 of e to the x. I pull my x to the front. So we have that. This log base 5 of e is some number. How do I find the derivative of 7x? 7. How do I find the derivative of x times log base 5 of e? Log base 5 of e, it's just a number times x, right? So its derivative is just the number. So when I take the derivative, I have log base 5 of x, which is going to be 1 over x, natural log of 5. Got that one. And the other one's just going to be log base 5 of e. Done. Now, if you wanted to, you could do the change of base there. You could say, oh, that's natural log of e over natural log of 5. And what is natural log of e? 1. So you might see 1 over x natural log of 5 plus 1 over natural log of 5. So what do you think they would do in order to combine those? Common denominators, right? So they might have the answer as x plus 1 all over x natural log of 5. So see how many different ways they can rewrite things. It's very, very frustrating on the exam. I'll give you a practice test that I actually gave as a test a few years ago. And then I ended up majorly curving it just because the multiple choice was just so hard. They were actual AP questions. All right, so the last thing we're going to learn is called logarithmic differentiation. Yeah? When I took the derivative, yeah. All right. So logarithmic differentiation is a way of finding the derivative of any function. Okay, so if I look at number 1, and I tell you guys to take the derivative of number 1, would you have a panic attack?
Yes.
I would have a panic attack if I had to take the derivative because it involves product rule, right? Quotient rule, chain rule, chain rule.
Let's do this.
All right, you can do it if you want. You really want to go for it, you can, but it's going to be pretty intense. All right, so there is an easier way to do this. Logarithms are actually very, very useful in calculus. That's why we hit logarithms so hard in calculus, okay? So there's something called logarithmic differentiation. we know that logarithms are kind of magical in that if you have a product and a quotient and so on, we can change it into plus and minus, right? That's going to be very useful for us in this problem. So what we're going to do for logarithmic differentiation is we start with some kind of crazy function that we're like, I don't know how to take the derivative of that, or I don't want to. And then I take the natural log of both sides. So when I do that, I can break up my logarithm into natural log of x to the 2/3 plus natural log of x to the 4th minus 1 to the 1/2 minus natural log of 5x minus 1 to the 3. Okay, and I still don't really want to take the derivative of natural log of x to the 2/3, right? So what can I do? Yeah, pull those exponents to the front. So I get 2/3 times natural log of x, which is very easy to take the derivative of. So I get this. So now that I've taken the natural log everywhere, and I've broken it down as much as possible, right, I expanded it as much as possible, now I take the derivative. And I take the derivative implicitly. So the derivative of natural log of y is going to be 1 over y, and since it was a y term, I tack on that dy over dx. Oh, implicit differentiation is not that bad. All right, now what about 2/3 times natural log of x? What do I get? 2/3 times 1 over x, exactly. What about the next one? I get 1/2 times 1 over x to the 4th minus 1 times 4x cubed, right, the chain. And then I have minus 3 times 1 over 5x minus 1 times 5. Yep. So I clean it up a little bit. Yes.
Why are you taking 1 over y times dy over dx?
Because the derivative of natural log of a y term is going to be 1 over y, but since it's a y, you need the dy over dx. It's implicit differentiation, remember? So I'm going to have 2 over 3x plus the 1/2 and 4 reduce out to 2. So I'm going to have 2x cubed over x to the 4th minus 1 minus 15 over 5x minus 1. And then I want dy over dx, so what's the last step I have to do? Divide by 1 over y, which is the same as multiplying by y. So just tack on a y at the end. Now, maybe the AP test puts in the ridiculous thing that y is equal to, right? Or maybe they just leave it as y. Okay, a lot of times they'll plug it in, but usually they're much simpler, like the next problem. So here's the next problem. We have y equals x to the square root of x. This is not a form that we know. We've never talked about a variable raised to another variable. We don't know how to take the derivative of this, right? We don't know how to do it. It's not the power rule. You can't do that because it's not like a number that it's raised to. And it's not the, the a to the x rule, a to the x natural log of a, because it's not a base of a number, okay?
Yes.
So how do we do this? We do this with logarithmic differentiation. Sometimes it's the only way we know how to take the derivative. So I'm going to do natural log of y equals natural log of x raised to the square root of x, which allows you to pull the square root of x to the front. Now I can take the derivative, right? If you want to rewrite that as x to the 1/2, you could, but we'll go ahead and take the derivative. So I have 1 over y dy over dx equals square root of x times the derivative of natural log of x, 1 over x, plus, what's the derivative of square root of x?
Negative 1 over 2 root x.
1 over 2 root x, or 1/2 x to the negative 1/2.
Negative 1 over 2 root x.
Nope.
No, you're right.
And then natural log of x, like that. So you can combine. So we have dy over dx equals, you could write square root of x over x, or you could reduce, like, x is really square root of x, so it reduces out to 1 over root x. If you wanted to get, like, common denominators or anything with this other one. So we have that, and then we're going to multiply by y. Now this is one where the AP test would probably plug in y because y is so easy to write. Like they would probably just have that as the answer. So you can do that if you would like as well. But on the homework, if you just want to leave it as y, I'm fine with that. All right, and the very last one. So if I take the natural log of both sides, I bring the 1/4 to the front. All right, and I'm going to break apart that natural log. I don't want to have to do the quotient rule to take the derivative of that inside, right? I don't want to do that. So I'm going to break it apart. So I'm going to have 1/4, and then I'm going to have natural log of x squared plus 1 minus the natural log of x squared minus 1. So that 1/4 goes to both of them. So I'm going to have natural log of y equals 1/4 times the natural log of x squared plus 1 minus 1/4 times the natural log of x squared minus 1. Okay, now I'm ready to take the derivative. So we get 1 over y dy over dx equals 1/4 1 over x squared plus 1 times 2x minus 1/4 1 over x squared minus 1 times 2x. So like the 2 and the 4 reduce out a little bit. So we get x over 2 times x squared plus 1 minus x over 2 times x squared minus 1. We'll put that in a big bracket and we'll multiply by 1. So that's our answer. So see how that works? It's kind of weird when you first learn logarithmic differentiation. I remember not liking it in high school. It's really not like super hard though. It's nice because it makes things easier. So you should like it, but I know it's weird at first.